At Introduction to Rational Expressions, the first lesson here in Unit 3. The idea here is we're going to look at, we're going to build on what we've learned in expressions, and in particular in polynomials, and we're going to apply that to rational expressions. So here you'll learn how to determine where a rational expression is, when a rational expression is undefined in particular, and how to find its domain. Okay, so first of all, what is a rational expression? Like we said in the previous unit, a polynomial is an expression that consists of a sum of terms containing integer powers. Okay, so a quadratic would be a polynomial, like the 3x squared minus 6x minus 1. Other examples of higher degrees might include something like, say, 4x to the 5th minus 3x squared plus 2x minus 4. Okay, so this polynomial here just has a higher degree. Now, the key idea here when we look at rational expressions is all we're looking at, as you might imagine from the word rational, is that we're looking at a quotient of two polynomials. So basically we're going to create a fraction where both the numerator and the denominator are polynomials. So here's a few examples right here. A simple example, 1 over x. Of course, 1 is an expression, and it's a monomial, but it's a term right there. And x, of course, is its own term as well. So this is a rational expression. Okay, you've got an expression both in the numerator and the denominator. It is quite simple, but it's still a rational expression. Slightly more complex ones. All right, x plus 5 over x squared minus 4x plus 4. Okay, so you've got a binomial divided by a quadratic. Right? You can get even more interesting with the third example here, x times x plus 1 times 2x minus 3. See that it's broken up into various different factors already, whereas the quadratic down here is not. Okay, so the key idea here is that the numerator can be a constant and the polynomials can be varying degrees, and in multiple forms you can have a lot of different things showing up in rational expressions. Now, there's a few things we need to be aware of, okay? And the first of these is the undefined values, right? So we take a look at this expression, 2x plus 3 over x minus 2, right? So this expression, right, we can determine this value, we can determine the value of this expression for various different x values. You can plug in a value for x. Let's say we plug in 1 for x, okay? If we plug in 1 for x, then we get 2 times 1 plus 3 over 1 minus 2. Okay, and of course that solves to be 2 plus 3 over 1 minus 2 is negative 1. And so we get ourselves 5 over negative 1, or simply negative 5. We've solved that for negative 5. We're all good. We're happy. Okay. What if we plug in the value 2 for this expression? Let's take a look at what that looks like. 2 times 2 plus 3 over 2 minus 2. Okay. Now we can spend all our time. All we like. I'm going to leave the denominator for a second and just solve the top. This is 2 times 2 is 4 plus 3 is 7. Okay, and then we look at 2 minus 2. Well, as you can see here, this is 7 over 0, and that is undefined, right? Right? We cannot divide by 0. That's a problem. So what we say here, right? We'll see. We'll scroll down and take a look at it. What we say here is that this expression 2x plus 3 divided by x minus 2 is undefined when x is equal to 0. So we would stipulate that x is not equal to 0 would be one of our conditions, right? To being allowed to use this rational expression. So let's take a look at what that looks like. Okay, so that leads us into the idea of domain. Okay, so the domain of any expression is a set of all possible input values. It's something we've looked at before. This is all the possible values you can plug into an expression. And as we saw in that previous example there, we were unable to plug 2 into that expression and keep it true. Okay, so with rational expressions, we can put any value in for x, or in for the variable, except a value that would make the denominator equal to 0. So that's what we saw in the previous example, so because division by 0 is not defined. Okay, so the domain of a rational expression includes all real numbers, except for those that make its denominator 0. Okay, so here's another example here for us. Let's find the domain. Let's find the domain of x plus 1 over x minus 3 times x plus 4. Well, we can find the zeros of the denominator. So notice that this expression in the denominator, so x minus 3 times x plus 4, okay, can be equal to 0 in two situations. If x minus 3 equals 0, or x plus 4 equals 0, right? So that's because of the factor. So if x minus 3 equals 0, then we would get 0 times x plus 4, which would give us 0. If x plus 4 was equal to 0, we get x minus 3 times 0, and that is equal to 0 as well. Okay, so let's look at how that plays out. Okay, so x minus 3 equals 0. If we add 3 to both sides, we get ourselves x equals 3. So if x equals 3, that is a value we cannot use, all right? Okay, we'll see that in a second, okay? This second one here, if we subtract 4 from both sides, right, just using our algebraic method here, we get x equals negative 4, right? So here's our two values right here. Our two values where the domain, where the rational expression would be undefined, okay? So let's take a look at defining that. So we write the domain is the set of, so the domain is all values of x, or all real numbers, where x is not equal to 3 or negative 4, right? So all we've said here is that our domain for this is x is not equal to 3 and x is not equal to negative 4. We could always also write this expression. We could say x is not equal to 3 or negative 4. Okay, that would be another way of putting it in there, right? Okay, let's take a look at a few more examples. All right, find the domain of the following. So we're going to, there we go. So the domain of the following. So the idea here with this one here is, again, we're looking at all real numbers, but we've got to make sure that the denominator is not equal to 0. So we're going to kind of ignore the numerator here, right? Where the denominator cannot be equal to 0. So x minus 7 cannot be equal to 0. So we're looking at the set of all real numbers. Another way of writing this. So the set of all real numbers I like showing you ways of using shorthand. So the set of all real numbers is given by this strange looking R. Okay, so you can use this strange looking R as meaning the set of all real numbers. That's what it means, the set of all. So that's what that strange looking R means, right? The set of all real numbers. So we can say that the domain of this, we can say that x is an element, so that's this word, this here, x is an element of R. So x is in the set of all real numbers, but x is not equal to 7. All right, so there's our domain. We just wrote it in shorthand, right? So this symbol here so that means I'll put that in there as well. So this symbol here is that is defined as is an element of. All right, or is in, if you like, right? So x is an element of the set of all real numbers, or x is in the set. Sorry, we'll put that as it is in, right? That's another way of saying is an element of. So x is in the set of all real numbers, and x is not equal to 7. So that's our domain right there. Okay, very nice, quick and easy way of writing it when we define those two mathematical symbols, which are extremely useful. Okay, so a little bit of calculation here to make, right? We're looking for x to be equal to 0 here. Okay, so how do we make x equal 0? All right, well, let's solve this expression here for x first. So let's look at 2x plus 1. And we're actually looking for this to be equal to 0, right? So what is x, how do we make x equal to 0 here? So we just subtract 1 from both sides, all right? We subtract 1 from both sides, and that gives us 2x equals -1. And so divide by 2 on both sides. That's going to give us x equals -1/2, right? So what would make the denominator equal to 0 is that if x is equal to 1/2. So with all this said, x is therefore in the set of all real numbers, but x is not equal to -1/2. Okay, let's look at this third example here. The third example here is quite interesting because we can say here immediately, because it's factored, we can say that x is equal to 0. If x is equal to 0, so if x equals 0, then x times x plus 1 equals 0. But we can also say if x is equal to -1, because -1 plus 1 is equal to 0, then x times x plus 1 will also be equal to 0. Okay, so with all that said, we can say that x is in the set of all real numbers, but x is not equal to 0 or -1. So x is the expression is undefined at 0 or -1. All right, so domain, given the domain for each of those. Okay, so let's look at a quadratic example. Okay, so here we have a quadratic. All right, so recall that to find the zeros of a quadratic, you want to first find the you want to factor it. Okay, so we're looking for so let's start by factoring it. Okay, so we're looking for the factors of -8 that add up to -4. So we're going to have a positive and a negative. Right? The factors of -8 that add up to -2, well, that's going to be 4 and 2. And the 4 is going to be the -1 because we've got a negative here. So because 2 minus 4 is -2. So here's our two factors, right? Our two factors. And then from there, we find that to make one factor equal to 0, right, then x would be equal to -2. And to make the other factor equal to 0, x would be equal to 4, right? So here's our two zeros, right? And therefore, based on that information, we can now say that x, so this expression here is defined for all x in the set of all real numbers, except for x is not equal to -2 or 4. So let's take a look at this last example now here as well. Okay, so we're looking for the denominator to be equal to 0. So let's set that equal to 0. So x squared minus 4 equals 0. And we find, therefore, that if we add 4 to both sides, we get x squared equals 4. And so we're now required to take the square root of both sides to get x. And that gives us x equals plus or minus 2. Okay, so we can then say that this expression here, this rational expression, is defined for all x in the set of all real numbers, provided that x is not equal to -2 or +2. And that's what we're looking at here. So one last symbol that's very useful as well, just on the back of all this, is this upside down A. Upside down A, that means for all. Okay, so some awesome vocabulary that you're getting in this lesson here. Typically when we write for all x in R, so that's kind of, you might have heard me say for all a couple of times, and that's kind of where that's coming from. So you have, therefore, it's for all, okay? But that's just a side note. If you have any questions, please feel free to ask or leave them in the comments below.